Hello everyone. Last class I discussed about electromotive force and internal resistance. So internal resistance comes into picture. Suppose if you consider a cell. Suppose if I draw a cell circuit diagram. Suppose if you take this is a cell. So we added an internal resistance. So the cell consists EMF and along with the internal resistance R. So this everything is the circuit symbol for a cell. So EMF we define that EMF equal to work done per charge. So this is the work done by the source when there is no current drawn from the circuit. Or simply if you can take a cell and measure the potential difference, nothing is connected. So that we define as EMF or electromotive force. Its units also volt, joules per coulomb. And internal resistance occurs due to because of the motion of the ions and electrons within the electrolyte. So when the electrons and ions they are moving inside the electrolyte, so they will collide each other. So that occurs the reason for the internal resistance, and we end up by deriving an expression for the terminal potential difference. The terminal potential difference V equal to EMF minus I times R. So this is the I is the amount of current which is flowing through the cell, and R is the internal resistance, and E is the EMF, and V is the terminal potential difference. So here terminal potential difference, it is the potential drop across the cell when we connected the load. So by taking these concepts as basic concepts, today I would like to derive an expression for when cells are connected in series or when cells are connected in parallel. So let us see first series combination. Suppose if I take two cells, so this is first cell which is connected to another cell. So it is having EMF E1 and this is having EMF E2. So here I would like to represent internal resistance separately, not in the circuit, because that makes us to confusion. Suppose this cell is having internal resistance R1 and this cell is having internal resistance R2. So if I is the current is flowing through the cells. So if I consider to calculate the potential difference, so let me consider 2 points. So this is the point A and this is the point B. So along here if I consider, so this is another point C. Suppose if I draw an equivalent circuit, if we combine these two together, so when two cells are connected in series, obviously it became another cell. So instead of drawing two cells, I would like to draw an equivalent circuit. So this circuit exactly looks as same like this. So this is symbol of cell. So here I am having two end points, starting point and ending point A and C. And the same current I is flowing. Now here is the internal resistance R. Now here my task is what is to find the equivalent EMF, the total EMF of the combination of the cells, and I need to find the equivalent resistance, means the total resistance after combining the two cells. So these two things I need to find, and this will be the equivalent circuit for the given two cells. Suppose if I draw this with as highlighting, so this will becomes an equivalent circuit for that. Now how can I proceed to find the equivalent EMF and equivalent internal resistance? Suppose if I take, let V suffix A comma V suffix B and V sub C be the potentials at points capital A comma capital B and capital C. Now if V suffix A, V suffix B and V suffix B C are the potential at the corresponding points in there, so what could be the potential difference across the two cells? Now if I would like to find the potential difference, across the terminals of the two cells. So potential difference, I would like to find the 2 points at the first one, potential difference across VAB. So the potential difference formula, potential at B, or the difference we can write potential at A minus potential at B. So this is the potential difference for the first cell. So only the potential difference for the first cell. Since we remember this formula, potential difference formula, so the terminal potential difference of a cell V equal to EMF minus I times R. So that is the first cell. So if we can write the same expression for this, which also equal to, which gives to me, it is the first cell, E1 minus I times R1. I is the amount of current, same current is flowing to the two cells. So that is the expression for that. Similarly, if I write the potential difference between the points B and C, the potential difference between the points B and C equal to potential at B minus potential at C. So now in this case I need to take the second cell. So if I take the second cell, this is the second cell. So between the points B and C, now if you can write that expression for the potential difference, which is equal to, what can I get? That is the EMF of the second cell minus I times R2. So here I is the amount of current which is flowing through the circuit. E2 minus I times R2. R suffix 2. So to find the potential difference between the terminals of A and C, so in this equivalent circuit, I would like to find the potential difference terminals across the points A and point C. To find the potential difference across the terminals points A and C, so if we can see this, to find the potential difference across A and C, that is potential difference that is V of A suffix C is equal to, if you can closely see these two, if I combine these two potentials, so which is equal to potential at A minus potential at B plus potential at B minus potential at C. So if we combine these two, the potential minus B gets cancels. So we will get the potential at VA minus VC. Suppose that equal to, so these two values will cancel, VB and VB. So I will end up at here potential at between points A and C equal to VA minus VC, which also equal to, now on the right hand side we need to add up. So let me take this space. Now if I add at here, which equal to E1 minus I times R1 plus E2 minus I times R2. So when we add on left hand side, we're supposed to add on the right hand side. So if I rewrite this expression, so first I will write that EMF at 1 plus E1 plus E2 minus, if I take the common I of R1 plus R2. Now, so this is the potential difference across that two terminals A and C. That is the equivalent circuit. That's what we need to find it out. So this potential difference I would like to express as V suffix A C equal to, so the EMF of the equivalent circuit minus I times R equivalent. So here EMF equivalent value equal to E1 plus E2 and R equivalent value equal to R1 plus R2. Suppose if we connect N cells, suppose we connect N cells, if small n cells, are connected in series, so how this above expression changes? The potential difference will be between all the n cells. Suppose if I draw a diagram at here, so this is the first cell and second cell and third cell and so on, the last cell. So this is the nth cell, 1 2 3. Now if I connect the voltmeter to the two ends, so if I connect a voltmeter from this end to another end to know the potential difference, what is the expression for the potential difference if we connect voltmeter? So from this above expression, so this is what we connected, equivalent potential difference for the two cells. So for the n cells we will write the same expression. So for n cells the same potential difference. Suppose if I take, these are the 2 points as A and C, so the potential difference between the 2 points A and C equal to EMF of equivalent minus I times the internal resistance equivalence resistance. Now here we need to mention what are the EMF values. So the EMF equivalence, which equal to sum of the individual EMFs, E1 plus E2 plus E3 plus and so on up to nth cell. Similarly for the internal resistance of equivalence, internal resistance equal to R1 plus R2 plus R3 plus and so on R suffix n. So finally I will give the potential difference expression for n cells which are connected in series. So the potential the final terminal potential difference between the two cells equal to R equivalence. Sorry, E equivalence minus I times R equivalence. So this is the expression for the when cells are connected in series. Suppose what happens if cells in parallel? Cells in parallel. So let me draw the circuit diagram first. Suppose let me take two cells. So that is one cell. So these two cells are connected in parallel. So it means positive terminals are connected at one end and negative terminals are connected at another end. So this became parallel combination. So if I take 3 points at here, so this is the point A and this is point C. So our task is that to find the potential difference, terminal potential difference between the two ends V of AC. So let me take this is having EMF E1 and this is having EMF E2. And if we take the internal resistance, so internal resistance, if I draw separately, so this is internal resistance for cell 1, so that is R1. So this is R1 and this is internal resistance for the cell 2, so this is R2. Now in this parallel combination, if I is the current is flowing, the same I is current is also flows throughout the circuit, but at here junctions, so what happens, the current is dividing. So if I is current is coming at this junction, so let me take this junction as B2. So this junction I'll take as B1. When current is entering through a junction B2, so on the two ways current is supposed to pass. So if I1 is current which is flowing through first cell and I2 is the current which is flowing through the second cell, and same current also living through the cell, second cell, the same current here comes I2 and from the first cell here it comes as I1. Now at this junction again the total current combines. Now the same current I current will be the flows from the B1 to A. So due to because of the parallel combination, so here current gets divides. So if these two cells are connected in parallel, suppose if I would like to draw the equivalent circuit of this ones, equivalent circuit, it means instead of the two cells we will represent everything in a single cell. So we are having a single cell, so we need to find the potential difference between the locations A and C, so that is the end points. And here if it is parallel combination of these two cells, so here we will get EMF equivalence and internal resistance equivalence. The same current I flows through the 2 points A to C. So our task is to find the potential difference across the points A and C. So here very important point is that the total current I equal to sum of the individual currents I1 plus I2. So by taking this as a basic point at here, if I proceed, now we need to find the potential difference across the individual cells. So the potential difference, the PD across first cell, the potential difference across first cell equal to, so the first cell, if I can represent that as across the first cell, I will highlight with this. So we need to find the potential difference first across the first cell only. So if we call the potential difference as V equal to, so here it is representing as potential difference. It means the VB2 minus VB1. If you connect the voltmeter across the points, so what is the potential difference it will show? So that will be the potential difference across the first cell. So what is the potential difference formula? We will write the same for the first cell, that equal to EMF of the first cell minus current in the first cell, here it is I1, times the internal resistance in the first cell, that equal to R1. So from this expression, if I can write at here current I1 equal to, if you can rewrite this expression, I will write it down so that it's better for the understanding. So here V equal to E1 minus I1 times R1. So rearrange the terms and write the expression for I1. So if we can write I1 times R1 equal to EMF E1 minus V, terminal potential difference. Therefore I1 equal to E1 minus V upon R1. So this is the amount of the current which is flowing through the first circuit. So I1 equal to EMF of the first cell minus potential difference across the first cell upon internal resistance R1. Now likely if you find the potential difference across the second cell, so the potential difference across the second cell. So if you remember, so in parallel combination the potential remains constant, it do not be changes. So if I can take the same symbol for the potential difference, V equal to, so here equal to VB2 minus VB1. So here it's better to mention to me as second cell of EMF, so that the things will be gets easy. Second cell of EMF E2. So that equal to V equal to VB2 minus VB1. So let me do the same at here. So the potential difference of first cell of EMF E1. So then we can understand that in parallel combination the potential difference remains constant. So we will get the same notation for the potential difference. So here VB2 minus VB1 for the second cell. So it means if I connect a voltmeter across the second cell, now if I can take, so I am highlighting this at here, if I can connect the voltmeter across the second cell, so what is the potential difference shows by the voltmeter? So that we need to write in the form of the expression. The same, the potential difference formula at here. Here in this case it becomes EMF of second cell minus I2. Here I2 is the amount of the current which is flowing in the second cell times internal resistance R2. Therefore V equal to E2 minus I2 times R2, EMF E2. So now write the expression for current I2 equal to, so here I can get EMF E2 minus V upon R2. So this is the amount of the current which is flowing through the second cell I2. Now since we know that the total current I equal to sum of the individual currents, Suppose if I take this is first expression and this is second expression, and if you can add up, since I equal to I1 plus I2, therefore add up these two expressions. For I1 I can get that E1 minus V upon R1, EMF E1 minus V upon R1, and I2 plus EMF E2 minus V upon R2. So from this expression we need to figure it out what is the value of V. So that is our terminal potential difference across the two ends. So we will rewrite this expression. So I equal to E1 upon R1 minus V upon R2 plus E2 EMF E2 upon R2 minus V upon R2. So let us rearrange. I equal to E1 upon R1 plus E2 upon R2 minus V of 1 by, here it is supposed to R1. I take minus common in these two terms. So in these two terms V is common factor. You will take it minus V as common. So in the denominator I can get as 1 upon R1 plus 1 upon R2. So our task is to find the potential V. So we can exchange the terms. So I can bring this term this side, V of 1 upon R1 plus 1 upon R2 equal to E1 upon R1 plus E2 upon R2 minus I. If you further simplify, V equal to, so E1 upon R1 plus E2 upon R2 minus I upon, just write that the denominator term. So it is 1 over R1 plus 1 over R2. So if we can do the simplification and if we can write the final expression. So after taking the LCM and do that everything, so we can get the final expression V equal to, so I can do the LCM on the numerator, so that equal to E1 R2 plus E2 R1 upon R1 and R2 minus I upon, on the denominator also we can do the LCM. So if you can do the LCM on at here, I will get that here R1 plus R2 upon R1 R2. Okay. Now if you can divide this with the each terms, now we can get that V equal to E1 R2 plus E2 R1 upon R1 R2 whole divided by R1 plus R2 upon R1 R2. So here it is minus, and there I can get that I of I upon R1 plus R2 upon R1 R2. Just I split the two terms. Now we eliminate the common in the denominator, R1 R2 gets cancelled, and finally we write that expression V equal to E1 R2 plus E2 R1 upon R1 plus R2 minus I, if I do this reciprocal, I of R1 R2 upon R1 plus R2. So this is the final expression for the potential difference when we connect the cells are in series and cells are in parallel. So this, if I can rewrite like this expression appears to very big, so I will shrink it to small. So this term I can express as E equivalent minus I times, and this expressions we represent that as R equivalent. So when n cells are connected, so this expression will little changes. So this is the final expression for the potential difference if two cells are connected in parallel. So here we can write what is the EMF equivalent. The value of EMF equivalent here EMF equivalent value equal to E1 R2 plus E2 R1 upon R1 plus R2, and R equivalent equal to R1 R2 upon R1 plus R2. So we can express the above expression in a simpler way. So the above expression can express also can express like this. So this is another way to express by rearranging the terms. So EMF equivalent upon R equivalent is equal to E1 upon R1 plus E2 upon R2. Instead of remembering that everything, and we can remember these small things very easily. So if we can do the LCM, we can get the same thing. So nothing to worry that. So I can write this as 1 over R1 plus 1 over R2. So this is the handy expression to remember. And not only that, it will becomes very easy when it comes to all n number of cells are in parallel. Suppose n cells are connected in parallel. If n cells are connected in parallel, so how we can write the equivalent expression? EMF equivalent upon R equivalent equal to, so that is E1 by R1 plus E2 by R2 and plus and so on En by Rn. Similarly for the R equivalence, so that I can write that as 1 over R equivalence equal to 1 by R1 plus 1 by R2 plus and so on 1 upon Rn. So this is the final expression for the EMF. So this is the expression, but I would like to encourage you remember this R equivalence upon E equivalence to find the terminal potential difference of a cell which are connected in parallel. So anyway, this expression it won't change, the form of the expression it won't change, but only the EMF for the n cells when connected in the series and when connected in the parallel, so that term only gets changed. So if you do practice 2-3 times, so it will be easy.